in a windowless room buried deep beneath the Swiss countryside. Physicist Dr. Francois Bouchet stares at a screen displaying the most detailed map of the early universe ever created. The data streaming from the Planck Space Observatory shows temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang itself, captured when the universe was only 380,000 years old. These tiny fluctuations, differing by mere millionths of a degree, represent the seeds from which every galaxy, every star, every planet in the observable cosmos would eventually grow. But as Bouchet analyzes the data, he notices something troubling. The mathematical models that perfectly predict the universe's infancy fail to explain what we observe today. According to these calculations, the cosmos should still be birthing massive galaxy clusters, still weaving new threads into the cosmic web that connects all matter across space. Instead, astronomical surveys reveal a universe that appears to have stopped growing sometime in the distant past. The largest structures we observe today seem frozen in time, relics of a more creative epoch that ended billions of years ago. This discovery forces us to confront a profound question about the nature of cosmic evolution. When did the universe transition from an era of explosive growth and creation to one of gradual decay and dissolution? And more importantly, what does this transition mean for the future of complexity, consciousness, and life itself in an aging cosmos? The story begins 13.8 billion years ago, not with a bang but with a whisper, the gentlest possible emergence of space and time from a quantum vacuum. In the first fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation, stretching tiny quantum fluctuations to astronomical scales. These primordial ripples would become the scaffolding upon which all future structure would be built. When inflation ended, the universe was filled with an almost perfectly smooth soup of elementary particles and radiation, heated to temperatures of trillions of degrees. For the first 380,000 years, matter and energy were locked in a cosmic tug-of-war, with photons scattering endlessly off free electrons in a dense plasma that rendered space completely opaque. The universe glowed like the surface of a star, but that light could travel no further than a few centimeters before being absorbed and re-emitted in a different direction. Then came the moment cosmologists call recombination, not because anything was recombining, but because for the first time in cosmic history, electrons were combining with atomic nuclei to form neutral atoms. As the expanding universe cooled below 3,000 degrees Kelvin, the cosmic plasma suddenly became transparent. Light could finally travel freely through space, carrying with it a snapshot of the universe's infancy that we observe today as the cosmic microwave background radiation. Dr. Vera Rubin, working in the 1970s with photographic plates from distant spiral galaxies, was among the first to realize that this smooth beginning couldn't possibly explain the complex structures we observe today. Her measurements of galactic rotation curves revealed that galaxies contain far more mass than can be accounted for by visible stars and gas. This invisible mass, what we now call dark matter, makes up approximately 85% of all matter in the universe. Dark matter doesn't interact with light, making it impossible to observe directly. But its gravitational influence shapes the evolution of cosmic structure on the largest scales. Computer simulations show that without dark matter, the tiny density fluctuations imprinted during cosmic inflation would never have grown large enough to form galaxies and stars. Dark matter provides the invisible scaffolding that allows ordinary matter to collapse and condense into the complex structures we observe today. The Millennium Simulation, one of the largest computer models of cosmic evolution ever created, traces the gravitational dance of 10 billion dark matter particles across 13.8 billion years of cosmic history. The simulation reveals how the universe's largest structures emerge from the interplay between gravity, which pulls matter together, and cosmic expansion, which stretches space apart. In the early universe, gravity dominates, allowing small density fluctuations to grow exponentially. But as space expands and matter becomes more dilute, expansion eventually wins, preventing new large-scale structures from forming. This cosmic arms race between gravity and expansion reaches a turning point approximately 7 billion years after the Big Bang, when the universe is about half its current age. At this critical moment, a mysterious force called dark energy begins to dominate cosmic evolution. Dark energy acts like anti-gravity, accelerating the expansion of space itself and making it increasingly difficult for matter to collapse under its own gravitational attraction. The discovery of dark energy came as a complete surprise to the astronomical community. In 1998, two teams of astronomers studying distant supernovae expected to find that cosmic expansion was slowing down under the gravitational influence of matter. Instead, they discovered that the expansion rate has been accelerating for the past 5 billion years. This acceleration is attributed to dark energy, a hypothetical form of energy that permeates all of space and drives cosmic expansion at an ever-increasing rate. Dr. Saul Perlmutter, one of the Nobel Prize winners who discovered cosmic acceleration, often describes the moment his team realized what their data was telling them. "We kept checking our calculations, convinced we had made an error," he recalls. The idea that the universe's expansion was speeding up seemed to violate everything we thought we knew about gravity and cosmic evolution. But the evidence was undeniable. We were witnessing the universe transition from a matter-dominated era to a dark energy-dominated era. This transition represents one of the most significant phase changes in cosmic history. During the matter-dominated era, which lasted from about 50,000 years after the Big Bang until approximately 5 billion years ago, gravity was the dominant force shaping cosmic evolution. Dark matter halos grew larger and more massive, pulling in ordinary matter that could cool and condense to form the first stars and galaxies. The cosmic web, a vast network of filaments connecting galaxy clusters across billions of light years, emerged during this period as matter flowed along the paths of least resistance carved out by dark matter's gravitational influence. But once dark energy began driving accelerated expansion, the rules of cosmic evolution changed fundamentally. Existing structures could continue to evolve and mature, but the formation of entirely new large-scale structures became increasingly rare. The cosmic web stopped growing. Galaxy clusters reached their maximum sizes and began to separate from one another as space expanded between them. The Sloan Digital Sky Survey, the largest three-dimensional map of the universe ever created, provides compelling evidence for this transition. By measuring the distances and velocities of over 1 million galaxies, astronomers have traced the cosmic web in unprecedented detail. The survey reveals that the largest structures in today's universe, superclusters spanning hundreds of millions of light years, are not actively growing, but instead represent frozen remnants of structure formation from an earlier cosmic epoch. Dr. Michael Strauss, analyzing data from the Sloan survey, describes these observations as archaeological evidence of the universe's creative period. The distribution of galaxies we observe today preserves a record of cosmic structure formation that ended billions of years ago. "It's as if we're walking through the ruins of an ancient city," he explains. "We can see the grand architecture that was built long ago, but no new construction is taking place." This cessation of large-scale structure formation doesn't mean the universe has become entirely static. Within existing structures, evolution continues at a rapid pace. Galaxies still merge with their neighbors, triggered by gravitational interactions that were set in motion billions of years ago. Stars continue to form from gas clouds, though at a much slower rate than in the cosmic past. Supermassive black holes at galactic centers continue to grow, fed by occasional streams of matter that venture too close to their event horizons. But these ongoing processes are essentially the universe playing out scenarios that were established during its more creative period. The Milky Way's eventual collision with the Andromeda Galaxy, predicted to occur in approximately 4.5 billion years, represents the completion of a gravitational interaction that began when both galaxies first formed over 10 billion years ago. Similarly, the ongoing star formation in our galaxy's spiral arms represents the gradual consumption of gas reserves that were established during earlier epochs of cosmic evolution. The James Webb Space Telescope is now providing the most detailed view ever obtained of galaxies in the early universe, when large-scale structure formation was still active. Webb's infrared eyes can penetrate the cosmic dust that shrouds stellar nurseries, revealing galaxies in the process of assembling from smaller building blocks. These observations show a cosmos that was more chaotic, more dynamic, and more creative than the relatively sedate universe we inhabit today. Dr. Marcia Reek, principal investigator for Webb's near-infrared camera, describes the telescope's revelations as watching the universe in its youth. The earliest galaxies observed by Webb are irregular and gas-rich, caught in the act of rapid star formation and frequent mergers with their neighbors. Everything was happening faster in the early universe, she explains. Galaxies formed, evolved, and interacted on timescales that seem impossibly brief by today's standards. These observations reveal that the peak epoch of galaxy formation occurred when the universe was between 1 and 3 billion years old, long before our solar system existed. During this cosmic springtime, dark matter halos were still growing rapidly, pulling in vast streams of gas that fueled the formation of massive stellar populations. The intergalactic medium was denser and more turbulent, providing a continuous supply of raw materials for star formation and black hole growth. But this golden age of galaxy formation carried within it the seeds of its own destruction. The massive stars that illuminated these early galaxies lived fast and died young, exploding as supernovae that heated and dispersed the surrounding gas. The supermassive black holes that powered brilliant quasars grew fat on accreting matter, eventually becoming so luminous that their radiation pressure blew away nearby gas clouds. Most importantly, the universe's accelerating expansion began to stretch space faster than gravity could pull new matter into existing structures. The Illustris simulation, a sophisticated computer model that tracks both dark matter and ordinary matter through cosmic time, shows how these various processes combine to shut down large-scale structure formation. The simulation reveals that by about 7 billion years after the Big Bang, the cosmic web had essentially reached its final configuration. While individual galaxies continued to evolve within this framework, no new filaments or superclusters could form. Dr. Mark Vogelsberger, who helped create the Illustris simulation, compares this transition to a phase change in physics. Just as water vapor condenses into liquid droplets at a specific temperature, the universe underwent a kind of crystallization process, he explains. The cosmic web froze into its current configuration, with future evolution limited to changes within existing structures, rather than the creation of entirely new large-scale patterns. This cosmic crystallization has profound implications for the future of complexity and consciousness in the universe. During the active structure formation epoch, the cosmos was constantly creating new environments where complex chemistry could occur. Colliding galaxies triggered bursts of star formation that enriched space with heavy elements. Merging dark matter halos created new gravitational wells where gas could collect and condense. The universe was essentially terraforming itself, creating an ever-growing number of sites where complexity could emerge. Once large-scale structure formation ended, this cosmic terraforming process largely ceased. The universe entered what we might call a conservation phase, where existing structures mature and evolve, but new ones are rarely created. This doesn't necessarily mean that complexity stops increasing. Biological evolution on Earth, for example, has produced organisms of extraordinary sophistication long after our galaxy reached maturity. But it does suggest that the universe's capacity for creating entirely new types of complex structures may be fundamentally limited. The search for extraterrestrial life takes on new urgency in light of these cosmic constraints. If the universe's creative period is largely over, then the habitable environments that exist today may represent the final flowering of cosmic complexity. The planets orbiting nearby stars, the subsurface oceans of icy moons, the complex organic chemistry occurring in stellar nurseries. These may be the last great laboratories where life can emerge and evolve. Dr. Sarah Seeger, pioneering the search for biosignatures in exoplanet atmospheres, often emphasizes the temporal dimension of astrobiology. We may be living during a brief window when complex chemistry and biological evolution are still possible on cosmic scales, she notes. If we don't find life in the universe soon, we may never find it at all, not because it doesn't exist, but because we're approaching the end of the epoch when it can emerge. The transiting exoplanet survey satellite has discovered thousands of worlds orbiting other stars, many of them potentially habitable. But the vast majority of these planets exist in systems that formed billions of years ago, during the universe's more creative period. The red dwarf stars that host many potentially habitable worlds are so long-lived that any life evolving around them would have vast amounts of time to develop. But they would also be isolated in an increasingly empty universe, as cosmic expansion carries other galaxies beyond the horizon of observation. This cosmic loneliness represents perhaps the most poignant aspect of the universe's transition from growth to conservation. Future civilizations, no matter how advanced, will inherit a cosmos that appears much emptier and more static than the one we observe today. The rich tapestry of galaxy clusters, cosmic filaments, and active galactic nuclei that fills our current view of the universe will gradually fade as expansion carries these structures beyond the observable horizon. Dr. Lawrence Krauss, contemplating the far future of cosmic evolution, describes this process as cosmic Alzheimer's disease. The universe will essentially lose its memory of its own history, as the evidence of past structure formation disappears beyond the cosmic event horizon. Future astronomers will look up at the night sky and see only the stars in their local galaxy group, he explains. They'll have no way of knowing that space was once filled with billions of other galaxies, no evidence that the universe underwent a period of rapid structure formation. But perhaps this cosmic forgetting also represents a kind of mercy. If consciousness persists into the far future, it will inherit a universe that appears stable and eternal rather than one obviously in decline. The gradual fading of cosmic structure may be so slow that it remains imperceptible even to civilizations that survive for millions or billions of years. The Event Horizon Telescope's recent images of supermassive black holes provide a glimpse of what may be the universe's ultimate fate. These cosmic monsters, sitting at the centers of galaxies, represent the final stage of gravitational collapse, regions where matter has become so concentrated that not even light can escape. In the far future, after stars have exhausted their nuclear fuel and planets have been stripped of their atmospheres, black holes may be the only remaining reservoirs of organized matter in the universe. Dr. Katie Bauman, who developed the algorithms that made the first black hole image possible, often reflects on the cosmic significance of these objects. Black holes are like cosmic time capsules, she explains. They preserve information about the matter that formed them, even as they slowly evaporate through Hawking radiation. In some sense, they may be the universe's way of remembering its own history even as everything else fades away. The theory of Hawking radiation suggests that black holes are not truly eternal, but slowly evaporate by emitting particles into the surrounding space. For stellar mass black holes, this process takes an incomprehensibly long time, longer than the current age of the universe by many orders of magnitude. But eventually, even the most massive black holes will disappear, leaving behind only a cold, empty universe filled with elementary particles and radiation. This ultimate fate, what physicists call the heat death of the universe, represents the final victory of expansion over gravity, of entropy over organization. But it also raises profound questions about the nature of information and consciousness in the cosmos. If the universe's organizational capacity is fundamentally limited by its expansion and cooling, what does this mean for the long-term prospects of complex systems like life and intelligence? Some theoretical physicists, including Dr. Freeman Dyson and Dr. Frank Tipler, have proposed that advanced civilizations might find ways to survive even the heat death of the universe. Perhaps consciousness could be uploaded into quantum computational systems that operate more efficiently as the universe grows colder. Perhaps the fundamental constants of physics allow for forms of organization and information processing that we haven't yet discovered. Others, like Dr. Sean Carroll, argue that the universe's trajectory toward maximum entropy is irreversible, and that all complex structures, including consciousness, are fundamentally temporary. From this perspective, The cessation of large-scale structure formation represents the beginning of the end, a cosmic sunset that will eventually extinguish all forms of organization and complexity. The cosmic microwave background, that ancient light from the universe's infancy, continues to cool as space expands. Today, it has a temperature of 2.7 degrees above absolute zero. In the far future, it will approach absolute zero itself, taking with it the last vestige of the universe's hot, dense beginning. When that happens, the cosmos will have completed its transition from a state of maximum organization to one of maximum entropy. Yet even as we contemplate this ultimate cosmic fate, we must remember that we are witnessing something unprecedented in the universe's history. For the first time, matter has organized itself into patterns sophisticated enough to understand their own cosmic context. We are the universe's way of knowing itself, conscious observers capable of tracing the great arc of cosmic evolution from its explosive beginning to its quiet end. The cessation of large-scale structure formation may mark the end of the universe's ability to create new types of complexity on cosmic scales. But within existing structures, complexity continues to increase. Life on Earth has become more sophisticated over time, not less. Human civilization has developed technologies that allow us to observe and understand cosmic evolution on unprecedented scales. We have become participants in the cosmic story, not just passive observers of it. Perhaps the universe's transition from growth to conservation doesn't represent decline but maturation. Like a forest that stops adding new trees, but continues to develop more complex ecological relationships among existing organisms. The cosmos may be entering a phase where sophistication matters more than scale. The grand architecture of galaxy clusters and cosmic filaments may be complete, but the detailed structures within this framework, planetary systems, biological ecosystems, technological civilizations, may still have vast potential for growth and development. The question of when the universe stopped growing new galaxies thus becomes a question about our own place in cosmic history. Are we living in the twilight of cosmic creativity, witnessing the last flickering candles in an increasingly dark and empty universe? Or are we experiencing the dawn of a new phase of cosmic evolution, one where consciousness and complexity can flourish within the stable framework established by billions of years of structure formation? The answer may depend not just on the physics of cosmic expansion and dark energy, but on the choices made by conscious beings throughout the universe. If intelligence is sufficiently widespread and sufficiently advanced, it may find ways to continue the universe's creative work even after the natural processes of structure formation have ceased. Conscious observers might become the universe's way of transcending its own physical limitations, creating new forms of organization and complexity that would be impossible through gravity and thermodynamics alone. In this view, the end of large-scale structure formation doesn't represent cosmic death but cosmic birth, the moment when the universe transitions from unconscious physical processes to conscious technological ones. The scaffolding of dark matter and cosmic expansion has provided a stable platform for complexity to emerge. Now it falls to consciousness itself to determine what will be built upon that foundation. As we peer deeper into space with ever more sophisticated instruments, as we decode the cosmic microwave background and map the distribution of dark matter, as we search for signs of life around distant stars, we are participating in the universe's attempt to understand and perhaps transcend its own limitations. We are the cosmos asking questions about itself, wondering whether its period of growth is truly over or just beginning a new phase. The answer lies not just in the stars, but in ourselves.